Assalamu alaikum everyone. So welcome to our first class after the mid exam, and we will start our topic from AC voltage controller in power electronics course. I will cover the book of Harun Rashid in chapter number 6. So what is basically AC voltage controller is that the purpose of the voltage controller is to control the output voltage. So if we have a input AC voltage and if you want to control the output RMS voltage of this input AC voltage, then you can use AC voltage controller. We may also need to control the frequency of our input voltage for various applications. In that case we also use the AC voltage controller. So the most common application of voltage controller is industrial heating and on-load transformer tap changers for controlling the lights and speed control of motors. So we know that the motor speed is related to the equation 120 F by P, where F is the frequency of the source voltage and P is the number of the poles. So that means that if we want to change the speed of the motors, then we need to change or we need to control the frequency. And this particular section in power electronics course will deal with this part, that how we can control the frequency as well as how we can control the voltage. Okay, so first let's start with the on-off control and the phase control. So basically there are two types of controls that are used for controlling the AC voltage. One is the first one is the on-off control. We have already discussed it in our discussion classes in the discussion class last week. So in the on-off control, basically we have a thyristor. This thyristor switches is turned on for several cycles and then it is turned off for several for the rest of the cycles. So by doing this an on and off control, this is a very simplified version of control. So by doing this on and off, you can basically control the output voltage. Okay, so if you look at the circuit for on and off control, the circuit looks like this. So we have two anti-parallel thyristors here, and we give the gate pulse of the thyristor. For T1 it's G1 and for T2 it's G2, and you can see here that for the first two full cycles the gate pulses are applied in both thyristor T1 and T2, whereas in the third cycle there is no gate pulse applied. As a result, if we do not apply the trigger pulse in the thyristor, then it will not conduct. So even though it is forward biased, and if we do not apply any trigger pulse, it will not conduct. That means in the output you will not get any current. As a result, the output voltage will be 0. So this is the basic way of understanding the on-off control. So for certain time, for some cycles it will be on. That means you will give gate pulses in the thyristors, and then for certain cycles there will be no gate pulses in the thyristor, and the thyristors will be triggered at 0 degree. That means that the conduction will start just after the zero crossing. So there will be no phase delay, or there will be no phase controlling in this particular voltage controller. So what is the benefit of using such control is that, as you can notice here, that the current starts conducting from the angle 0 degree, and that means that if you do the Fourier analysis of this particular wave shapes, you will have reduced harmonics, in contrast to the case when you have a phase delay, and you trigger the thyristors after a phase delay. So that is the biggest advantage. So you basically reduce the harmonic contents in the circuit. Okay, so now let's try to understand that how we can derive the equations for the output voltage, the output RMS voltage. So if you are asked to calculate the output RMS voltage, then if you notice at the output here, so this is the output V out here. So this V out, this is the amount of cycle that is repeating every time. So this pattern is repeating. That means in the first 2 cycles you have a current conduction. That means the output voltage will be the same as the input voltage for the first 2 cycles, and in the third cycle, in this particular case, is 0, and this pattern is repeating. So the time when these thyristors are turned on is defined as N, and for the time when it is turned off is defined as M. So if you calculate the RMS value of such a wave shapes, that means that if you go here, that means that the RMS is the square root. So that means the first comes the square root of everything, and then you integrate it for the whole cycle, so from 0 until here, and that corresponds that you integrate N multiplied by the time. So it is N multiplied by root 2 Vs sine omega t whole square, which corresponds to 2 Vs square sine square omega t, and then for the whole time you divide it for the whole time, which corresponds to both N plus M. So it corresponds to N plus M multiplied by twice pi. So this is the RMS, this is the expression for the output RMS voltage, and if you do the simplifications, you end up with Vs square root of N divided by M plus N, which is also defined as root over K, or in this particular case K is called the duty cycle. So thus you can see that as this value of K is always less than 1, that means you can control the output voltage. You can vary the output voltage from 0 until Vs, or the source voltage. Okay, so let's try to address a numerical problem that is shown here. So a AC voltage controller in figure 6.1 has a resistance has a resistive load of 10 ohm, and the RMS input voltage is 120 volt, 60 Hz. The thyristor switch is on for N is equals to 25 cycles and off for M equals to 75 cycles. Determine the RMS output voltage, V out, input power factor, and the average and RMS current of the thyristors. So it is given that R is equals to 10 ohm. So this R corresponds to 10 ohm, and then Vs is 120 volt, and Vm is root 2 multiplied by 120. So it's given here. So this is the RMS of the input voltage. That means that the peak of the input voltage is root 2 multiplied by 120 volt, which corresponds to 169, and then K is N divided by N plus M, which is 0.25, and it is asked to calculate the RMS output voltage. So just now we have derived the equation for output RMS voltage, and V out is actually Vs, or the source voltage, multiplied by the square root of K, which is 0.25. So 0.25 multiplied by 120 corresponds to 60 volt, and it says the input power factor. So we calculated the output voltage, and to calculate the input power factor, that means the what is the power factor of this circuit from here. If you look at from here, then the power factor is basically the actual power, which is P out here, which is the load, the power consumed in the load. And to calculate the power consumed in the load, we need to calculate what's the output current, and the output current I out can be written as V out divided by R. So in this particular case, our output voltage is 60 volt and the resistance, the load resistance is 10, so our output current is 6 ampere. So our output power is I square R, which is 360 watt, and since the input current is the same as the load current, the input volt ampere is VSIS, or 120 multiplied by 6. This is because if you look at here, your input current, the IS, the current that is coming in, is the same as the output current, and it is only when the thyristors are on you will have the output current, and that means that the output current is 6 amp, just as you calculated here. So your input current is also 6 amp, so your input volt ampere is 120 multiplied by 6, which is close to 720 watt. So the input power factor is this output power divided by input volt ampere, which corresponds to this 360 divided by 720, corresponds to 0.5, and this is lagging because our current here is lagging actually. Okay, so and the third question, it says that what's the average and the RMS current of the thyristor. So if you look at the thyristor current, so if you look at the thyristor current, then you can derive the expression for the average and the RMS value of the thyristor current as well. Okay, so the peak thyristor current is 169.7 divided by 10, 16.97 ampere, and the average current of the thyristor is, you get the thyristor current equation and you integrate it for the whole period, and in this particular case this is n. So this is for the n times n number of cycles this thyristor is turned on, so this should be n multiplied by Im sine omega t, and the whole time you divide it by the whole time period, which is twice pi multiplied by m plus n, and you integrate it from 0 to pi here. Okay, and after simplifications and if you replace the values, then you will get the actual current values here. And the RMS current of the thyristor is the same, so the thyristor is turned on for the n number of cycles, so that means that you have to integrate it for the whole 100 cycle. In this particular cases, n corresponds to 25 and m corresponds to 75, but instead, as this is repeating, so we what we do is that we integrate it for 0 to pi and we multiply it by the number n, because for the number n we have a value and for the number m the output is 0. So the RMS output current in the thyristor is, first we do the square root and then n multiplied by, for the one single cycle it is for 0 to pi Im sine omega t, and you square it, so as I square sine square omega t divided by the whole time period, which corresponds to twice pi multiplied by m plus n, and you do the simplifications after that to get the actual current value. Okay, so the on off control is pretty simple and straightforward. So what you have to do is that if I recap it again, so your thyristor is allowed to turn on for certain cycles, and for certain cycles it is turned off, and thus by doing so you control the output RMS value. This particular kind of arrangement is quite useful in industrial heatings. Okay, so the next one is the phase control. So the term phase control, as it says, it is that it is done by firing the thyristor or by triggering the thyristor at a phase angle which is higher than 0 degree. So you control the phase angle here, the firing angle of the thyristor, and by controlling the firing angle of the thyristor you control the output voltage. So the idea is very simple, and there are several different kinds of controllers. The simplest one is unidirectional controller, and in this particular arrangement we have a thyristor and a diode. So if you want to use only one thyristor, then you can use this circuit, but the challenge or the issue with this particular arrangement is that you do not have controllability in the other half cycle, so you can only control it for the one half cycle, and hence its name is unidirectional control, because you can only control in one direction. In the other direction you do not have any controllability. So in this particular case, this thyristor T1 is triggered after the firing angle alpha. So after alpha, this thyristor T1 is triggered, and hence the current starts flowing after that, and it continues to flow until the thyristor current is 0. And as this is a resistive load, so this output current will be will follow the voltage. That means that the current and the voltage zero crossing will be exactly at the same place, and as a result this thyristor will cease to conduct at 180 degree, and after 180 degree the polarity will reverse in the input. So this will be negative and this will be positive, and then this diode will basically conduct. So the current will flow like this through the diode. Okay, so that is what you see it from here. So this is the current conduction in the diode. Okay, but the issue, as I said, that the challenge here is that you do not have any controllability in the other part, or in the other half cycle. Okay, so for this particular arrangement, if you need to calculate the RMS output voltage, the RMS output voltage is the square root. First comes the square root terms, and then for the whole cycle is 1/2 pi. So it's 1/2 pi from alpha to pi, because the current starts conducting from alpha. So from alpha to pi it is √2 Vs sine omega t whole square, plus from pi to twice pi is √2 Vs sine omega t whole square. So if you integrate it, you calculate the value of the RMS output voltage, and for the average value of the output voltage, it is the equation for the average, which is 1/2 pi, and then you integrate it from alpha to pi, √2 Vs sine omega t, plus integrate it from pi to twice pi, √2 Vs sine omega t. Okay, so here is another numerical problem. It is exactly the same one like before. It says that the load resistance is 10 ohm and the input voltage is 120 volts, 60 hertz. The delay angle in the thyristor alpha is pi/2, that means it's 90 degree. Determine the RMS value of the output voltage V out. So from the equation, as you can see here, from the equation the output RMS value is 1/2 pi, and then twice pi minus alpha here is pi/2, so you can replace alpha with pi/2, and then you will be able to calculate what is the V out here. And the RMS load current is simply output voltage divided by the resistance, because it's a resistive load, so your output current is V out divided by R. And the load power is I square R, so our P out is simply I square R. So the input power factor, which is equals to output power divided by the input volt ampere ratings, and the input volt ampere rating is the output current is the same as the input current, so our output current multiplied by the voltage here, so this is 1247, and you have to calculate the power factor, you have to divide this output power or the load power divided by the input volt ampere ratings, which is equals to 1079 divided by 1247, and that will also be a lagging power factor, because if you look at here, so the current is lagging here. If you do the Fourier analysis, you will see that the fundamental component will have a current that will lag than the voltage. So the input current will lag the input voltage. Okay, and the third part, it says to calculate the average input current. So to calculate the average input current, it's the same as the average output. So you calculate it from the average output voltage, which is 120 multiplied by √2 divided by twice pi, and then the average input current is simply VDC divided by R. Okay, yes, so it comes from here. Okay, the next thing is the single phase instead of unidirectional controller. Now we will discuss about the bidirectional controller for resistive load. So when we have a resistive load and we have a bidirectional controller, means that we have two thyristors in anti-parallel direction, and you can control both of these thyristors independently to achieve a certain output RMS voltage. So in this particular case, again our delay angle is alpha, so after alpha we are triggering these thyristors. So the first half cycle will be like this, that after alpha the current will start conducting here, and if you notice here, then you can see that this rise of the current is very fast. That means if you do the Fourier analysis here, then you will find a higher harmonic contents in this particular current compared to on-off control. This is will have higher harmonic contents. Okay, so the equation for the output RMS voltage is again it's square root of 1 over twice pi, and then you have from alpha to pi you have this repeating 2 times, so this and this is the same, and that is why you have 2 here, and then this is √2 Vs sin omega t square, which corresponds to 2 Vs square sin square omega t, and you apply the integration and trigonometric formulas to calculate the output RMS voltage. Okay, now this particular circuit has a challenge, is that you have to drive these 2 thyristors from 2 different sources, and then this cathode should be isolated from one another. That means that if you have a common grounding, so if you have a driving circuit like this and you have a common grounding here, then you cannot connect this common grounding to this thyristor, and you cannot use the common grounding with this thyristor. You cannot connect it like this, because if you do, then you are basically shorting these two paths. That means that you are basically shorting these two terminals, which is why you are not allowed to do that. And for that reason, you can use two different so you have to connect two different driving circuits here. So gating circuits of the thyristors must be isolated, and to avoid this complexity of the driving circuits, you can rearrange it in this way. And in this particular case, that you have two thyristors connected, the cathode of these two thyristors are connected at the same point, so that when you give a trigger pulse, a positive here, I think I made a mistake here. So here is our, let's say, the driving circuit. The positive terminal is connected to this node, and then this is the cathode. So with respect to this, you have to apply the negative voltage. So this is the negative, and then if you apply the common ground, if you have the common ground, that means that this terminal will also be connected here. So which you cannot do, because if you do, then you are basically shorting this path. That means that you need to have isolation between these two drivers, and as a result, you normally have to have two different drivers to drive these two thyristors. And if you want to use the common ground arrangement, then what you have to do is that if you want to have a common terminal for both of these thyristors, then you arrange it like this. So basically, in this case, your cathodes are shorted, so you can have a common ground here, and then you can trigger this thyristor, and after some time you can trigger this one, so you can have a single control circuit to drive the thyristors. But the expense here is that you need additional two diodes connected in this way. So how this circuit is operating is that in the positive half cycle, so when this terminal is positive and this terminal is negative, at that time the current is flowing like this, and you trigger the thyristor after time alpha, and the current flows like this. It's like this and goes, and then after the current zero crossing, this thyristor ceases to conduct, and then the polarity reverses, so the current starts flowing like this, and it goes through these thyristors and through this diode and leaves. So this is the benefit of using this particular circuit, is that you can use the same driver circuit to drive both of these thyristors, but with the expense of having more diodes, and the another expense is also the losses in the circuit. So as you have more components, so previously in this particular case you have the losses, the current was only flowing through thyristors, so the losses were coming only from the thyristors, but now it will come from the thyristors as well as diodes. So the efficiency of this circuit will be lower than the efficiency of this particular arrangement. Okay. There is another arrangement that can be used if you want to use one thyristors, then you can have a bidirectional control using one thyristors with four diode arrangements. So in this particular arrangement, for the positive half cycle, the current will flow through diode D1 and through thyristor T1. So once you trigger at alpha, thyristor T1 will start conduct, and then it will pass through D2 and then through the load, and in the negative half cycle the polarity will be reversed, so this part becomes positive and this part becomes negative, and the current will flow through the load and then through diode D3 and then through thyristor T1 through D4, and it leaves like this. So this is how the output voltage wave shape is, and from the output calculation it is exactly the same as it's shown here, but the only difference here is that you have more components now. You need 4 diodes and 1 thyristors, as well as this particular arrangement will also increase the losses, as in this particular case the current will flow through in each half cycle. It will flow through 2 of these diodes and 1 thyristors, resulting in higher losses, but at the expense that you can design the circuit with only 1 thyristor. So exactly the same numerical problem is also here, so you can go through these numerical problems, and if you have still problems you can discuss it in the discussion classes. The next one is interesting because now the load is not resistive, rather we are having an inductive load, and if the load is inductive, then the thyristor doesn't cease conduct at the source voltages 0 crossing. It doesn't cease conduct because the current through the thyristor is still flowing. So whenever you have for instance in the positive half cycle, it is positive and negative, so the current was flowing like this, and once you trigger the thyristor it's flowing through both R and L, and L is resisting the change in the current flow. So this once you have a voltage 0 crossing of the source voltage, this L will continue to push this current in this way, so the current will flow through the thyristors, and until this current becomes 0 in the thyristors, this T1 will be turned on. So basically the output voltage will depend on the alpha, so it will depend on alpha as well as the power factor here. So this ratio between omega L and R we will see. Okay, so that means that it will not stop conduct at unlike the resistive load case, it will not stop conduct at 180 degree, rather it will conduct even more than that. Now depending on the value of this L and R, this the time of the moment when it ceases conduct will be defined. Okay, so unlike in the resistive circuits where your gate pulse can only be a very short duration pulse, in the case of a inductive load this cannot be a short duration pulse, because if you have a short duration pulse, and that means that once your if your current is still conducting and you have a short duration pulse, and it may happen that you once the current in thyristor T1 comes to 0, at that time the short duration pulse is goes down, so the thyristor T2 will not be triggered, so it should be a continuous pulse, so ideally like this. So if you do not want to miss the trigger here, that should be ideally continuous. But having a continuous gate pulse will also increase the losses in the circuit, because you are continuously giving a gate pulse here, it will generate more losses to avoid this situation, normally what is done in practice is that there is a train of short pulses that is being applied in the gate. So in case if one of the pulses is missed, then the next one at the next one the thyristor can be triggered, and by doing so you also reduce the losses in the circuit. Okay, so if you look at here, is that in practice most loads are inductive in certain extent. A full wave controller with RL loads is shown here, and T1 is fired as the positive half cycle and carries the load current. Due to the inductance of the circuit, T1 may not fall to 0 at omega is equals to omega t is equals to pi. This is very, very important, because if it is inductive load, then it will not become thyristor 1 will not cease conduct at omega t is equals to pi when the input voltage starts to be negative. Rather, it will continue to conduct until the current in the thyristors becomes 0. At omega t is equals to beta is called the extinction angle. So the moment when this thyristor T1 ceases conduct is defined as beta, and the conduction angle delta is basically the difference between beta minus alpha. So the moment when it starts conducting and the moment when it ceases conduct, the difference between these two is the conduction angle, and it depends on the delay angle alpha. So it depends on the firing angle of the thyristor alpha and the power factor of the load theta. So theta is basically the ratio of the inductive impedance and the resistive load. So theta is tan inverse omega L divided by R. So if our Vs, or the input voltage, is √2 Vs sin omega t, then the current in the thyristor can be written as L di dt plus Ri. So once this thyristor T1 is on, at that time if you apply KVL, then your input voltage is equals to Ri plus L di dt. So you get an equation like this. So the solution of this differential equation is √2 Vs divided by Z sin omega t minus theta plus A1 e to the power minus R divided by L t. So if you use the rule for solving this differential equation, then you can find the solution of this equation in this form. But here A1 is unknown, and to find the value of the A1 you need to know the initial condition of A1, and the initial condition of A1 can be determined at the moment when alpha, so just at alpha, when this thyristor T1 is being triggered, that means when T1 is triggered, then this KVL is you are applying this KVL, and at that moment, just before that, there was no current flowing through here, so I was 0, so I1 was 0. So if you apply I1, so if you apply this as 0, if you put I1 is equals to 0, and if you replace omega t with alpha, so if you replace omega t with alpha, then you get this equation, and then you can calculate the value of A1. So and then if you replace the value of A1 with equation 6.13, then you end up with the current equation in the thyristors, which is I1 is the equation like this. So the angle beta when current I1 falls to 0 and the thyristor 1 is turned off can be found from the condition where I1 omega t is equals to beta is 0. So at beta omega t is equals to beta, this current is also 0, and from there you can get this equation here. So because I1 will be 0 at omega t is equals to beta, so if you place this one as 0, and then sine of omega t means beta minus theta will be equals to sine of alpha minus theta e to the power r divided by L, and alpha minus beta divided by omega. So you replace omega t with beta, so you multiply it with t on both sides, and then you end up with this. So this extinction angle alpha can be determined in an iterative approach. So, and from that once you calculate the value of beta, you can calculate the conduction angle delta by subtracting beta. From beta subtract alpha, you get the conduction angle delta. So the RMS output voltage is 1 over twice pi, and as you have this output voltage from alpha to beta repeating 2 times, so here comes 2 and then root 2 Vs sine omega t, you square it and you find 2 Vs square sine square omega t from alpha to beta, and you square root it for the whole time. And by doing the manipulation, you end up with the output RMS value. The RMS thyristor current can be found from equation 15. So you have the current equation here, and from current equation you can calculate the output thyristor RMS current. So the thyristor RMS current is from alpha to beta 1 over twice pi alpha to beta I1 square, and you square root everything here. Okay, so once you know the RMS current of one of the thyristors, you can calculate the output RMS load current, and in the same way you can calculate the average thyristor current as well. Okay, so yes, so what is the relation of alpha and the theta, this load angle theta, is that if your alpha is equals to theta, at that time your conduction angle becomes pi, or beta minus theta, this becomes pi. And for the case when alpha is less than theta, so if it is a purely inductive load, then theta is 90 degree, and if alpha is less than this theta, at that time the gate pulses of the thyristors, and if the gate pulses of the thyristors are long duration, the load current would not change with alpha. So alpha has no impact on changing the load current, and both thyristors would conduct. Thyristor T1 would turn on at omega t is equals to theta, and thyristor T2 would turn on at omega t is equals to pi plus theta. And how it's happening is that if you have alpha value less than theta, that means that it will continue to conduct until theta, and at theta it will, if there is a continuous gate pulse, if there is a gate pulse for a long duration, then at theta the thyristor pi plus theta, the thyristor T2 will turn on, and this will repeat. We will see it in a short simulation. So the controlling for controlling purposes, if because if alpha is less than theta, we basically do not have the load current, do not have any impact on alpha. That means we can no longer control the output load RMS value, load voltage. So to have the controllability, our alpha should lie within the range of theta and pi, so it should be higher than theta and less than pi. So here is a very short model that is being built here. So this is our input voltage. So in this particular case, I put the frequency at 50 Hertz, the peak amplitude at 100 volt, and then I'm measuring the input voltage. So here is the input voltage, so this can be write as V in here. So this is going to the output, and then we have two thyristors placed in anti-parallel direction. So let's first see the how the phase control is working for a resistive load. So if we change this load to a resistive load and place this value as 1, so this is our load, and then we're measuring the load current here. So this is our load current, and this is the load voltage. So number 4 will show the load voltage in the scope, and then we have two anti-parallel thyristors here, which has a trigger pulse here, and the trigger pulse has a frequency of 1/50. So 50 is the frequency is 50 Hertz, so the time period is 1/50, and then I'm having a phase delay of 2 millisecond. So normally for 50 Hertz cycle, our whole half cycle is 10 millisecond, so we are having alpha is basically 2 millisecond, this delay in the firing angle, and that means this thyristor should have a phase delay of 12 millisecond, because half cycle is 10 plus 2 millisecond is the phase delay, and our pulse width is 40% because this is repeating. So yeah, and then we are also measuring the both of these thyristor currents, and then we are measuring the voltage across the thyristor. So very simple circuit, and if we run it for 1 second in case of a resistive load, let's see how the circuit actually looks like. There's a lot of values here. Let's put this 0.1. Yes, so this is our gate pulse. So as you if you notice it here, the pulse generator 1 is the yellow one, so this is on, and then you have a delay alpha, and after that you turn the second thyristor on. This is our input voltage, and this yellow one, this is 100 volt amplitude here. And if you notice that the thyristor, the yellow one, the thyristor 1 starts conducting when you give the trigger here. So when you give the trigger here, thyristor 1 starts to conduct. And before that, when the thyristor 1 is not conducting, the voltage as the thyristor is not conducting, so the source voltage is appearing across the thyristor for that moment. So if you measure the voltage across the thyristor, you will measure the source voltage is exactly following the thyristor voltage is actually following the source voltage. And at that time, as there is no current flowing from 0 to alpha, as there is no current flowing through the thyristor, so the output voltage is going to be 0. And once from alpha, the output voltage will be exactly as the source voltage, and it will continue until the current continues to flow. So in this particular case, as this is a resistive load, so the current will continue to flow until 180 degree. So this is pretty easy to understand, but what happens if we change the load from resistive to an inductive load. So let's add another load here and then replace it with L. Now this particular resistance is 1 ohm. So first let's start with a lower value of the inductance. So our omega is twice pi f, and which corresponds to twice pi f means is 314. So if this is let's say 1 e to the power minus 4, so if we have a calculator here, so that means then 314 divided by 10,000, which is 0.03, much lower compared to the resistive load. So the inductive part is much lower in this case. So what do we expect if we run it? We would expect that the current will not be the current zero crossing will not be at 180 degree, rather it will be delayed by certain time, but that delayed time will not be very much, because the inductance here, the value of the inductor is pretty small compared to the value of the resistance here. It should be R1. Okay, so if we run it, then we can see what happens here. Yes, so if you look at carefully, very carefully, then you can notice that that your current is not exactly at the voltage zero crossing. So it is not exactly at the voltage zero crossing, so it is a bit shifted. So a bit shifted, the current is a bit shifted towards the right, and as the current continues to flow, that means the thyristor is conducting. So at that time, as the thyristor is having a current, so your thyristor voltage will be 0 for the moment when you have a thyristor current. Okay, and if you look carefully, then this is also a bit shifted. So this is the current, and this is the voltage across the load. So now if we increase the inductance here, let's say we make it e to the power minus 3. So e to the power minus 3, this is that means that it's, let's make it comparable with our load. So we have 1 ohm, and then this is 314 divided by 1000, which means 0.314. So it's 1 divided by 0.314, 3.18. So if we place 3.18, that means that our omega L part is equal to our resistance part, and tan theta is 1, corresponds to theta is equals to 45 degree. So now see what happens here. So this particular case, our theta is 45 degree. So in terms of time, 360 degree corresponds to 20. So if I place the calculator here, so our 360 degree corresponds to 20 millisecond. Oh, sorry, so it should be it should be 20 divided by 360 and then multiplied by 45. So in terms of time it's 2.5 millisecond if the delay angle in our case now the alpha or the delay angle is 2 millisecond, which is smaller than the theta value. So in the book, as you have learned, that if alpha is less than theta at that time, and if the gate pulse of the thyristors are long duration, so as the gate pulses are set here for a long duration, which is 40% of the whole period, that means that the load current would not change with alpha. So for this particular condition, if we change the alpha, we will not have any change in the load current, and you see that the it is triggered here, and then have a look here. You see that this is the moment when the thyristor is triggered, but it starts conducting at theta. So it starts conducting at theta. So the conduction starts at theta and it doesn't depend on alpha. So as long as alpha is less than theta, the conduction starts at theta and it no longer depends on alpha. So let's see what's the amplitude of the output current. So this is our output current, and if we zoom in at the peak of the output current, then you can see that is around 70 amp in this particular case. And if we change this phase delay, let's say by 1, and if we replace this and 1 with 11, then the output current should also be 70 amp. So if you look at here, so the output current is 70 amp. Neglect the first one because the first one is the transient part. So in the steady state part, our output current is exactly 70 amp. So the output current does not depend on the firing angle alpha. So here if you look at the firing angle here, so for the whole time, so the firing starts here, but the thyristors start conducting at theta. That means that for the condition when your alpha is less than theta, you do not have any controllability of the output voltage. That means that you can no longer control the output current. So when you can control the output current is the moment when you have a delay angle higher than the theta value. So in this particular case, theta was 2.5 millisecond. So let's place it with 3 millisecond here. That means it should be 13 here, and then if we run it, then we see that now this conduction of the thyristors starts with alpha. So if you zoom in here, so this is our alpha, this is our triggering angle, and the thyristor starts conducting here. And before that, so this is the moment when we do not have any conduction in the thyristor, and at that time you have a voltage stress that is appearing in the thyristor, which is basically the same as the source voltage for that particular moment. Okay, so if you look at the YOLO curve in the pulse generator. So this is pulse generator, the trigger pulse for the thyristor 1. So when the thyristor 1 is triggered, and then at the source voltage current 0 crossing, you see that the thyristor current is not 0, is still continuing to conduct until the thyristor current becomes 0. After that, the T1 will turn off. So thyristor T1 will continue to conduct until the current in the thyristor becomes 0, and this is due to the effect of the inductance. So that's it for today's lecture. If you have any question, we will try to address it in the discussion classes. Thank you.